Hello and welcome. This is going to be our homework help video for the second trig quiz review. Let's get started with some of these simplifications. Problem number one, don't forget to look and see if some canceling can happen right off the bat. These cosines can cancel out. So if we get rid of those, this actually becomes pretty easy. This is just 1 over cotangent, which we know by one of our reciprocal identities is just equal to tangent. And when I say simplify, I want to get each of these expressions down to just a single trig function. So there we go. It is just now tangent. 1 minus cosine squared. Well, I could start like trying to rework this. It might be kind of difficult. What's a better option is to recognize that 2 of these elements come from our Pythagorean identity. So if I write my Pythagorean identity off to the side, I can change this to look like this, and then just do a single substitution. So this says 1 minus cosine squared. How can I make this look like 1 minus cosine squared? Just by subtracting cosine squared from both sides. Now I've got that sine squared equals 1 minus cosine squared. Therefore, if 1 minus cosine squared is equal to sine squared can replace 1 minus cosine squared. And this counts as just one trig function. We're never going to be able to get rid of that squared. But this is just one term versus 2 terms, so that's considered simplified. Number 3, sine times by the quotient identity, cosine over sine. Sines cancel out. This is just cosine. Problem number 4. Well, nothing jumps out right away as being able to cancel or a spot where I'm going to want to apply a Pythagorean identity. So I'm just going to decompose into sine and cosine. So I'll leave the sine and the cosine alone, but the cotangent I'll replace with cosine over sine. All right, to make this look better, I might make this a cosine over 1, so it's obvious that this cosine needs to multiply up here, giving us a new equation of sine plus cosine squared over sine. Now I'd like to combine these, but this has got a denominator of 1, and this has a denominator of sine. So I got to make those match. Easiest way to do that is to multiply this first one by sine over sine. Now I've got sine squared over sine plus cosine squared over sine. With that common denominator, I can now rewrite it with just a single fraction, sine squared plus cosine squared over sine. And that just equals 1 over sine. Because cosine squared plus sine squared plus cosine squared, look up at our Pythagorean identity, that is equal to 1. So right there, applying my Pythagorean identity. Up here, that was a quotient identity. But I'd like to take this down to just a single trig function. That's still a fraction, so I'm going to use a reciprocal identity on this. Turn that into cosecant of theta, but when I'm doing these problems, I generally don't write the theta. 5, 6, 7. I think these are all different enough that we should do them all. So let's go through this. Nothing's jumping out where I can easily cancel or apply a Pythagorean. So I'm going to decompose into sine and cosine. I've got cosine times by the quotient identity, cosine over sine plus sine equals 1 over sine. This cosine can go on top now, and this becomes cosine squared over sine. We run into that same problem where this is a sine over 1. So I'm going to multiply that by sine over sine to get a sine squared over sine equals 1 over sine. All right, so now I've got cosine squared plus sine squared over sine equals 1 over sine. And then by the Pythagorean identity, I can rewrite that cosine squared plus sine squared as a 1. So 1 over sine equals 1 over sine. So let's see, right there I used a quotient identity. Right here I used a reciprocal identity. And then right there I used a Pythagorean identity. Let's go back to the original equation to assess the domain of validity. I'm going to write each of these functions with the ratio they represent. Cosine is adjacent over hypotenuse. Cotangent is adjacent over opposite. Sine is opposite over hypotenuse, and cosecant is hypotenuse over opposite. The only side length that appears in the denominator is opposite. We ignore the hypotenuse because that's never 0. And opposite is equal to 0 at n pi, so we must exclude that from our domain by stating that x cannot equal n pi. Box there, little box there. All right, problem number 6. How am I going to verify this one? Well, don't see a spot where I can obviously apply the Pythagorean or do any canceling. So let's decompose into sine and cosine. Cotangent becomes cosine over sine. Minus 1 over cosecant is going to become 1 over sine. Equals, I can just leave this as cosine minus sine. All right. To simplify this fraction, I got to combine the top first, but this is just a 1. Why don't I replace that with something equivalent to 1 that has a common denominator with sine over here? I'm going to replace that 1 with a sine over sine, which is equivalent to 1. All right, now we've got common denominator, so I can subtract the tops there. Cosine minus sine over sine, all over 1 over sine, equals cosine minus sine. Copy dot flop, and we get cosine minus sine. Now, because that was together in one fraction, it can keep a set of parentheses. Over sine times, if I flip this up, bottom one upside down, it becomes a sine over 1. Notice how it flopped there. And because this is minuses in a set of parentheses, I'm still able to cancel my signs here. This 1 goes away, and now I've got cosine minus sine equals cosine minus sine. And back up to this, cotangent is adjacent over opposite, cosecant, hypotenuse over opposite. Cosine and sine both have hypotenuse in the denominator, so we want to exclude the exact same as the one above. X cannot equal n pi. All right, number 7. So I'm seeing some squareds, so that makes me feel like I could potentially apply Pythagorean, but I don't see any like +1s or -1s, which help those Pythagorean identities work. So I'm still just going to decompose number 7 into sine and cosine. So secant squared is going to become 1 over cosine squared. Cosecant squared is going to become 1 over sine squared. And over on this side, I'm going to get cosecant is 1 over sine squared. And I'm going to go ahead and just copy dot flop that for space. The cosine on the bottom is 1 over cosine. So when I flip that, or it's cosine squared over 1, so it becomes now 1 over cosine squared. After I do copy dot flop, and now this side is going to become 1 over sine squared cosine squared, and need to combine these two. So I multiply that first fraction by sine squared over sine squared. The second fraction by cosine squared over cosine squared. These are both forms of 1. And I'm going to combine this side. What's this going to look like? I'm going to have sine squared over sine squared cosine squared plus, running out of space, so I'm just going to combine the common denominators and put that plus cosine squared up top right now, equals 1 over sine squared cosine squared. And then this right here by the Pythagorean identity becomes equal to 1. So the final expression here is 1 over sine squared cosine squared equals 1 over sine squared cosine squared. I'll definitely leave more room on the quiz so you can show all that work neatly. I know this got a little messy. I skipped a couple steps in there, but if you were listening, hopefully you got all the steps to make that verification work. Let's just do the domain of validity real quick. Secant is hypotenuse over adjacent, but cosecant is hypotenuse over opposite. So I've got both opposites and adjacents in the denominator. So I need to exclude n pi over 2. And we already got up here that n is an element of the integers, so we don't have to define it again. All right, final solutions to each equation in radians, tangent of theta equals -1. So what I want to do here is turn this -1 into the fraction -1/1, which is also equal to 1 over -1. That's going to give me my opposite and my adjacent as I go to draw in this triangle. So let's get a coordinate plane. All right, if the opposite is 1 and the adjacent is -1, that's going to bring me right over here. So opposite's 1, adjacent's -1. I recognize that as a 45, 45, 90, meaning that this angle out here is 3 pi over 4. It's one of my answers. And then the other triangle is down over here with a adjacent of 1 and opposite of -1. But this angle always happens exactly 180 after this one here. So to state my answer, I just have to say theta equals 3 pi over 4 plus pi n. And then that will give me this angle. And then I'll rotate another half revolution. I'll get back to a coterminal angle here. Coterminal, coterminal, on and on and on. That is my solution for number 8. All right, when is cosine of theta equal to -√3/2? Well, if I get out my unit circle, and I remember that cosine of theta is the x value in the unit circle, I can probably find these. Let me actually get my unit circle. And I'm looking for when the x value is equal to -√3/2. And I've spotted one of them. It's right here at the angle of 5 pi over 6. So 5 pi over 6. Our x value is -√3/2. And the other one is 7 pi over 6 right there. All right, and then both of those need to get a plus 2 pi n, and you've got the full answer. All right, let's look at the back side. Number 10 is interesting. As I attempt to solve this, I might divide both sides by 3, get 2√3/3 equals sine of -3 pi plus pi over 3, and then try to take the inverse sine of both sides. But here's where I run into a problem. Let's just estimate 2√3/3. Root 3 is about 1.7, I want to say. Let me check that. Yeah, a little bit more than 1.7. So let's write this off to the side. 2 times 1.7/3. That's about equal to 3.4/3, which just really rough estimate is, I don't know, about 1.1. So it might be closer to 1.2, but it doesn't matter. All that matters is that this number here is bigger than 1. So if I try to take the inverse sine of a number bigger than 1, I'm going to get an error message. This has no solution. There is no angle I can plug in and get an opposite over hypotenuse bigger than 1. I'll explain that more down here on 13. Let's look at number 11, which does have a solution. I can just get rid of this -3, divide it over to the other side, and 0 divided by -3 is still 0. Let's take the inverse cosine of both sides. And again, so inverse cosine of 0. Again, I look for this x value in my unit circle. I'm going to see it twice here. Might not be at the first angles you look at. It's at pi over 2 and 3 pi over 2 is when cosine is equal to 0. This is one that we all just wrote down as a good one to memorize. This here can be expressed as pi over 2 plus pi n, because they're exactly 180 degrees apart. And then that is equal to -4 theta plus 5 pi over 4. I want to get theta by itself, so I subtract 5 pi over 4 from both sides. 5 pi over 4. Let's see, I could rewrite this as 2 pi over 4. So 2 pi over 4 minus 5 pi over 4 is going to be negative 3 pi over 4 plus pi n equals negative 4 theta. Divide everything by negative 4. And we get 3 pi over 16 plus, well, actually it's a minus, pi over 4 n equals theta. And that's our final answer. Let's take a look at the answer key at the end here. 3 pi over 16 minus pi n over 4. 3 pi over 16 minus pi n over 4. I brought the n out in front. That doesn't really matter. We should be able to pick the correct answer if we can get it to this point here. All right, number 12, we need to know what angle of elevation is. Angle of elevation, if I was to draw this out, let's see, like this. Angle of elevation is that angle right down there. From the ground to some line that is intersecting the ground. In this case, it's our eye line looking up at the top of the tower. This side over here is 2059. This side down here is 5280. All right, this is the opposite. This is the adjacent. Opposite and adjacent tells me that I want to use tangent. So tangent of theta equals opposite 2059 divided by adjacent 5280. Take the inverse tangent of both sides. And you get whatever that is. I think I remember it's like 21.3 degrees. Let's just check the answer key. 21.3. All right, why do I get an error message if I try to do inverse cosine of 2? Well, we can explain this a couple different ways. We could just say 2 is outside the domain of inverse cosine. Kind of a boring way to say it that doesn't really explain why I'm getting that error message, but technically correct, 2 is outside of the domain of inverse cosine. All right, more interesting is to say, well, this number here is supposed to represent adjacent over hypotenuse. All right, and I could fill in those values as 2 and 1. All that matters is that the adjacent is twice as long as the hypotenuse, so I can just go with 2 and 1. And if I try to draw this triangle, so let's just put an opposite out here. My adjacent is 2, so this is 2 for the adjacent. And now I've got a hypotenuse of 1. Well, that's not long enough to reach back to the opposite. Even if I lied it flat along the adjacent, it's still going to come up 1 unit short. So it's an impossible triangle. Therefore, I'm getting an error message. The other way to explain this is to say, well, the graph of cosine ranges from +1 down to -1. So from 1 to -1, and then back up again, and then down again, and then up again, and then down again. If I'm asking for the inverse cosine of 2, I'm asking for when this curve here hits the line y equals 2. Well, it's just never going to happen. If this is oscillating from 1 to -1, it will never go up to 2. Hence the error message, hence no solution. All right, so 14, domain of validity here. We want to write these all out as fractions, secant, hypotenuse over adjacent, cosecant, hypotenuse over opposite, tangent, opposite over adjacent. I have both types, adjacent and opposite, in the denominator. And at these angles, these guys become equal to 0. So these equal 0 when theta equals n pi over 2. And we can't divide by 0. I expect you to write more sentences than this, but I'm going to move on because I also talked about this one in class. Can't divide by 0. And these angles cause the trig functions to be equal to 0. And that's going to not make the equation balance. All right, so 15. Let's solve up 15 real quick. right off the bat, I see a good way to simplify. These 2 cosine thetas can just go away. Now I've got root 3 cosine theta plus 3 sine theta equals 0. I'm going to subtract 3 sine theta from both sides. So now I've got root 3 cosine theta equals -3 sine theta. Going to divide both sides by cosine of theta. On this side, it will cancel out. And on this side, by the quotient identity, sine theta over cosine theta will become equal to tangent. So root 3 equals negative root 3 tangent of theta. Move the -3 over. And I get negative root 3 over, or positive root 3 over -3. It doesn't really matter what that negative equals tangent of theta. This, I think, would be a good time to just use our all students take a calc diagram to kind of figure out what's going on. So I'm going to be in this quadrant and this quadrant where tangent is negative. And I need to draw my opposite equal to root 3 and my adjacent equal to -3. Or over in this quadrant, it would be opposite is negative root 3, adjacent is positive root 3. And you might not recognize this triangle right away. But if we were to do inverse tangent of root 3 over -3, we would get -30 degrees, which would correspond to this right here. And you might realize that this is our 30, 60, 90, but it's just been dilated a little bit. So our 30, 60, 90 goes 1, 2, and the square root of 3. Well, if I multiply every side by root 3, I can get a new triangle which goes 3, 2 root 3, and root 3. And now you see that this is actually a 30, 60, 90 with the 30 in there. All right, but I only actually need this first one. This first angle is 5 pi over 6. And then I can just say theta equals 5 pi over 6 plus pi n, because the feature of tangent is that the two solutions are always 180 degrees apart. So you can just say plus pi n and you get all the solutions. All right, well, that's pretty much the whole review. Good luck studying. Have a great rest of your day.